Good morning. This is Team 1 and my name is Jiwon Park. Today I will be talking about planning using probabilistic generative models. In planning tasks, there is no single correct answer. The desired trajectory can vary depending on goals or constraints given at each situation. Thus, this presentation will mainly discuss how to efficiently integrate such conditional information into the planning process. First, let me start by briefly explaining what probabilistic generative models are. These are models that learn the distribution of the data and generate new samples based on that learned distribution. And key operations include density estimation, approximating the true distribution of the data, and the sampling, generating new data points, and learning meaningful low-dimensional latent representation of the data. Now, why do we have to use probabilistic generative models in planning tasks? Planning tasks naturally involve several fundamental challenges like handling complex and high-dimensional environments, and managing uncertainty from noisy sensor information, and accommodating a wide range of possible outcomes and constraints. And probabilistic generative models are well suited for this purpose. They can model complex data distributions and explicitly capture uncertainty and condition outputs on specific contexts and produce diverse samples, all of which are critical capabilities for robust and flexible planning. And after DDPM was introduced in 2020, diffusion-based planning papers quickly gained popularity. And after diffuser provided a strong baseline pipeline, a large number of diffusion-based planning papers started to emerge. And then, starting from 2022, with the flow matching paper, we have seen a growing number of planning studies adopting flow matching methods, especially this year. Next, I will briefly revisit diffusion models. In simple terms, diffusion models work by gradually adding noise to data through a forward process and then learning a reverse process to recover the original data. And through this, diffusion models can capture highly complex data distributions with strong diversity and robustness. And there are a number of studies that adopted diffusion pipelines in planning and navigation tasks. For example, diffusion policy applies diffusion models to robotic manipulation by learning conditional trajectory distributions given task contexts. Or NOMAD formulates image-based navigation as a conditional diffusion process where the model generates trajectories conditioned on visual observations and goal information, enabling planning without an explicit map. And in both cases, planning is framed as sampling from a learned conditional distribution over trajectories. And let's take a moment to understand why diffusion models are particularly robust when applied to planning. First, diffusion models allow effective non-greedy planning. Because the sampling process starts from random noise, diffusion models can explain a wide range of possible solutions, increasing the likelihood of escaping local minima. And unlike traditional methods that often greedily optimize and can easily get stuck like gradient descents, diffusion models enable planning across long horizons while maintaining scalability. And this property is particularly advantageous for navigation and long horizon robotic planning. And now, let's see how conditions are handled in diffusion models. The term condition guides the generative process toward desired outputs. And during denoising, The model predicts the next step based not just on previous step but also on the condition C as shown in here. However, applying a condition alone is often not enough. We also perturb the generation using guide function as shown in like h tau, leading to a modified distribution. This approach softly steers the generation toward satisfying the condition without heavily distorting the learned distribution. During denoising, the model adjusts its prediction by adding a reward-based correction, and the updated mean is like this. And here, the J mu is the reward for the predicted trajectory, and this is the gradient. This shifts the sampling toward trajectories with higher rewards, guiding generation toward more desirable outcomes. And however, the DTG, the paper from 2024 IROS, takes a different approach. Instead of directly maximizing a reward, DTG applies an adaptive traversability loss during training. And this loss penalizes trajectories that enter non-traversable areas, effectively encouraging the model to generate feasible and safe paths. And as shown in the diagram, DTG starts from Gaussian noise and denoises through a conditional recurrent network, adaptively adjusting the trajectory at each step to satisfy traversability constraints. And the figure shows how DTG leads to a smooth and collision-free paths compared to other methods, while diffuser applies constraints during sampling through reward gradient guidance. DTG applies constraints during training by introducing a traversability loss. And next, I will introduce flow matching, another probabilistic generative model that has recently been gaining a lot of attention. And unlike diffusion models that progressively denoise random noise into samples, flow matching directly learns a continuous vector field that transports samples from a simple distribution, such as Gaussian, to the target distribution. In other words, instead of learning a step-by-step denoising process, flow matching focuses on learning the velocity field itself, which defines how to move particles continuously toward the desired distribution. And flow matching has also been applied to planning tasks. In particular, flow MP learns motion fields by applying conditional flow matching, where the model directly predicts the velocity field that transports trajectories toward the goal, conditioned on task-specific information. And the learned vector field is not restricted to a single type. It can represent different quantities depending on the formulation, such as basic motion field, an acceleration field, or even higher-order derivatives like jerk field, allowing greater flexibility in modeling complex dynamics. And in flow matching, the goal is to learn a vector field that continuously moves samples from the source to the target distribution. And this movement over time is described by an ordinary differential equation where the flow phi tx follows the velocity field vtx. And the ODE captures how each sample evolves over time, and by solving it, we can generate full trajectories that transform the initial distribution into the target. And training is done by minimizing the difference between the learned velocity and the ideal ground truth velocity at each point. Therefore, unlike diffusion models, which require many iterative denoising steps like gradually refined samples, flow matching directly learns a continuous transport map through a vector field. Because the entire transformation is defined by solving an ODE driven by the learned velocity field, in theory, flow matching can generate samples in a single integration step if the vector field is known precisely. Therefore, many flow matching papers highlight faster generation speed as a key advantage over diffusion models. This characteristic makes flow matching particularly appealing for real-time planning tasks, where fast inference time and real-time operation are critical requirements. And I would like to summarize the key difference between diffusion models and flow matching. Diffusion models use a step-by-step stochastic process with many sampling steps, while flow matching learns a deterministic velocity field for continuous transformation. As a result, diffusion excels at complex generation, and flow matching is better suited for fast and controllable planning. Thank you